Hi there. My name is Kyle Sword. I am the Manager of Business Development for NSG Pilkington here in North America. And today I'm going to be talking to you about the Momentum Intersection Program and give you a little bit of history about it. What is it? Why are we doing it? What are we hoping to achieve out of it? And it's been a really fun program. We've been doing this about 3 or 4 years now. So hopefully I'll share a little bit of insight as to who we are as a company and why this is so interesting for us. And thanks again for your time and participation. Today, I'm going to go over a little bit about our company, Pilkington, NSG, and LOF, Libby Owens Ford, among a dozen or so other glass companies. I'll talk a little bit about float glass manufacturing. That's how we make glass today, as well as some of the history. I'll talk a little bit about how those coatings that we put on the glass are applied and some of the different reasons that we would apply those coatings. We'll talk a little bit about some of the specialty applications that we make. And then again, what are some of the goals? What are we trying to accomplish with this program? So company has been around almost 200 years. It depends around the part of the world that you are. But in North America, we were a company called Libby Owens Ford. We date back to about 1898 here in the States, but in Europe in 1826 we actually started. So globally, a little bit of perspective. Pilkington started in the 1820s. Glass manufacturer, a variety of different glass manufacturing methods. Number of different glass manufacturers around the world also started around those times. We've had partnerships with all these different glass companies, for well over 100 years. And then as the industry morphed, a lot of those companies had mergers and takeovers and different things like that. So Libby Owens Ford got bought by Pilkington in the mid 80s. And then a group called the NSG Group in Japan bought Pilkington around 2006. So we've been around for quite a while, but in North America, we have 5 float lines, and I'll talk through float glass manufacturing shortly. And we're going to be starting our 6th float line here in about a month, which is pretty exciting. But the thing I want to tell you about our company is, being 200 years old, we've been at the forefront of glass and glazing technology for a couple hundred years. And about any way you could think of making glass, we've probably done. So we started as a crown glass manufacturer, and I'll go through some of these different processes in a bit. We started plate glass manufacturing. We did drawn cylinder glass. In the US here, a really big innovation is called the Colburn sheet glass process. Really revolutionized the residential world of construction. And that was an innovation within our company. We started doing laminated glass and tempered glass, and the float glass process was invented by Pilkington in Europe in the 1850s. We were sole sourcing GM windshields, in the 30s to the 60s, I think. So we've been around, and really innovation in glass manufacturing is kind of our core DNA. That's a lot of what we are and what we do. So I'll talk about the history of glass itself. How has glass been made, and try to give you a little bit of a flavor of what we do today and how that has changed historically. But most people think about glass melting, and artists especially think about it, and it's really about the melt itself. And to be honest, that's really where very little of our innovations have occurred. Taking a bunch of dirt and melting it in a big bucket, which is kind of what we do in a very large bucket, needless to say. That's a lot of what we've done, but most of those innovations have been really minor. So the big changes that have occurred in melting technology is essentially taking out all the really nasty bad stuff, but it's also stuff that gives you better properties. So these really vibrant colors, easy melting or longer working temps. A lot of these things that were used to be used caused cancer, and they really weren't good for your breathing and for your health. So over time, we've actually changed a lot of these. I think everyone knows about lead, and in drinking glasses, drinking lead's not great for you. So lead's no longer used to help work the glass temp. Things like arsenic were used as refining agents. And even today, I think products like nickel still sometimes get used. And there's these negative impacts called nickel sulfide inclusions that potentially cause glass to spontaneously explode. So there's all these things in glass that, that's not necessarily a safety of the glass itself, but how it's practically used. So we're continually getting better at just removing things in the melt process that are dangerous to people or not good for our products. But even in our manufacturing, asbestos used to be used as an insulation blanket in a lot of high temperature melting applications. Chromium brick was used. There's all these different things. So it's generally most of the innovations in our manufacturing process when it comes to melting have just been in using different types of materials. In the last about 50 years, there's been some innovations in other chemistries. We melt what's called soda lime glass. And that's what most drinking glasses, car, buildings are made out of, is soda lime glass. But there's some chemistries called borosilicates and aluminosilicates. That's things like Pyrex cookware, the high impact glass that's used in a lot of cell phones and touch screens. So those are some innovations that have been in the melt technology, but really soda lime glass is still, the workhorse of the different industries. But most development has been in the processing. So when I look at glass processing, most of it has been done to either streamline that process to make it easier, faster, cheaper to make, or it's to improve the optical quality. So the first thing I want you to look at is, how do we look at glass? And when we look at a piece of glass today, and this has been kind of the case for, maybe 50 years at least, but we'll take a very high intensity spotlight. So this is about 2 million candle watt power. You go in a dark room and you shine that on a piece of white paper, and then you stick the glass in between that light and the white paper, and you're looking for characteristics of the glass. And there's really three things that I look at when I look at a piece of old glass from, say, a 1950s building and say, well, how was this glass made? And I can probably tell you if I look at three things. So one is the surface texture itself. So if I look at the surface, what's the morphology? Is it rough? Does it have an orange peel effect? Is it bubbly? That tells you what the glass was in contact with when it was made, or maybe how the glass cooled. So you can kind of tell the processing from that. The second thing I look at is the surface shape. So when people talk about, their older 1950s Craftsman windows, and they really throw the light well, most times that's what you're seeing is these kind of light patterns and these dark patterns. That has to do with the thickness of the glass varies in that processing. And most times that's how it was actually made. But that thickness change and that shadowing effect can give you a good indication of how it was made. And the last thing that I look at is draw lines. So these are these kind of light and dark vertical and parallel lines, and that tends to indicate stretching process from a later stage, like industrialized manufacturing process. So dating back to about the 13th century, I mentioned our company started as a crown glass manufacturer, and this is really how we made glass back in the day. So you would take a big ball of glass, you would blow it into a ball, you would open that end up on it, and then stick it to a punty and then spin it. And you'd make these really large discs. These things were sometimes 6 feet in diameters. And then what you would do is you would cut rectangles out of the edges. And what you were left with in the center is called this crown bullion or cat's eye. There's a couple different terms, and that was kind of junk glass that went into cheaper homes, in the 13th century. That's really used as a neat architectural kind of motif now, as people design these doors to have these different crown bullions in them. But you made pretty nice windows out of these outside things. The thickness varied a lot. The surface was pretty clean, but it wasn't optically clear. So you really only can make small windows. So that was from the 13th century on to about the 17th century. And what you'll notice as I go through this, again, most processing developments are either how to make it from a batch to a continuous process, or how to make it better, less processing after you make it, to ultimately reduce cost on both of those things. So a slight derivation from crown glass is called cylinder glass manufacturing. There's still companies today like Lambert's and Bentheim that make this, but instead of just blowing a ball and then opening it up, you blow a really, really long cylinder, and then you cut the ends off and you split it lengthwise and heat it back up. You can make really large rectangles with this process. Typically what's sold today is 3 foot by 4 foot, but this was a really heavily industrialized manufactured product that really had these large industrial processes. So one was like a big steel tube that you had almost this bicycle pump that would pull a vacuum and suck the glass out to the edge. And the other way was these vertically drawn cylinders where you're pumping air into this thing as it's drawn vertically. And you can make really, really large cylinders, like, 10 foot long, 3 foot diameter, that made really, really big windows. So there's some really cool historical pictures that you'll see here. And if you look back through a lot of our books, a lot of North American and European books, what you'll see is, turn of the century, 1900s, there's all these pictures of the workforce. And in a lot of them, there's, 10 and 12, 15-year-old boys that are in the kind of the front rows. So again, I'm in no way advocating child labor. I'm not for these sort of things. But I will say, if you look historically at how a lot of these industries have developed, that was not uncommon that you would have these sort of things. So the reason I bring that up is just taking frame of reference when you look at other places in the world today and say, oh, look at that, and we would never do that. I hear that from a lot of people, and it's just not the case. I mean, to look back through the history of these things, but they actually would drive different types of processes to try and reduce labor and labor costs and make it easier to manufacture. Plate glass was a pretty major innovation when it came to commercial buildings. And the reason is to have a tall skyscraper, you really needed three types of products to kind of enable that technology. So you had to have air conditioning, you had to have elevators when you're talking 10, 20, 30-story buildings, and you had to have thicker plate glass in order to withstand the wind loads and the pressures that these high buildings have the demands on them. That, you know, a regular drawn cylinder glass was really, it was big enough, but it just wasn't strong enough to withstand the demands of commercial buildings. So the way this glass is made is you pour glass in between, like an old school washing machine, two squeegee rollers, and it would squeegee that onto a big steel plate. Or conversely, you could just dump it onto the plate and then run this roller across it. But you made really big sheets of glass, you know, 10 foot by 20 foot. And it typically had some sort of a diamond pattern in the bottom of it. And that was from where the contact with either the rollers or the steel plate came. And then you had to polish it. So the polishing process itself was a massive industrialized process. So most times you would take, you know, a 1/2 inch thick piece of glass, you would polish it for 4 hours on each side. You would take it from a 1/2 inch thick to a 1/4 inch thick. And, you know, it would take 8 hours. It would take dozens of people to do. So it was really expensive, but it was really nice quality. So this is what went on all skyscrapers. And if you had plate glass in your house, you know, you didn't see any distortions. It looked like the glass of today, but it was really, really expensive. So you were considered rich if you had plate glass. And that, you know, I'll go back to plate glass, 1800s in Europe, 1870s in the Eastern US. And then again, our company was started in 1898 here in Toledo. And we were one of the first couple companies that really started doing large scale plate glass in North America. Rolled glass was a very, very slight derivation from this. So instead of going from a roller onto a steel plate and doing it in a batch, this was a continuous process. You poured it out of a furnace onto a continuous roller bed. So again, nice quality. It still had to be polished, but now you're in a continuous process, so you take out a ton of cost. And sheet glass, I mentioned, major innovation. So this was super cool. This was done in Clarksburg, West Virginia. And you see on this left-hand picture, there's this like metal bar that goes across the bottom. And you would dip that into the furnace and then draw the glass vertically. So kind of similar to that cylinder drawn process, but more akin to the rolled process where it would cool a couple hundred degrees. And then it was cool enough that you would bend it 90 degrees and put it onto a continuous roller bed. What that created was it now was cool enough that you didn't leave a bunch of surface impacts on there. So you could take it directly off the line, not have to polish it, and put it into a house. This is that on that top right picture is a vertical drawn piece of glass. And this is what it looked like on the bottom right. So optically really clear, had a little bit of distortions that came along with it from that thickness variation. But you're starting to see draw lines. It wasn't thick enough and strong enough to really deal with the commercial buildings, but really every residential house after the 1920s pretty much had this product. It took out so much cost and it was still such a nice product that really just revolutionized the residential industry. And then float glass, that's what we make today. This is taking that molten glass, melting it, pouring it onto a bed of liquid tin. And what you then do is cool it from 2000 degrees to 1000 degrees. And floating on that tin, because it's lighter, the glass is lighter than the tin, you can make it super flat. You can make it really optically clear, cool it down to about 1100 degrees. And now when you put it onto a roller bed, you get almost no impact of the steel or the rollers at all. Really optically clear, doesn't have to be polished at all, continuous process, takes out tons of cost, makes a really high quality product. And that's what we do today. There's a video that I'm going to share with you that you can look at, but really we are a massive energy intensive operation. A new float line might be 500,000 to 1 million square foot. The furnace itself is about a 7,000 square foot ranch house that is 4 feet deep in molten glass. We have a couple $1 million worth of tin just to actually float the glass onto. We put up, 600 tons of glass a day. The scale of one of these float lines is really just impressive. So hopefully you guys will get a chance where you can actually come do one of our tours. They are very, very cool. But it's heavy industrial, huge manufacturing. That's what we do today. So the process that we make, all these raw materials, we mix them together, add a little bit of water, dump them into the furnace. We heat it up to about 2,800, 2,900 degrees, dump it into the furnace, it starts to melt. It might take 8 hours to a week to really get a good melting process. But you can see this is what that furnace inside looks like. I tell people it's the gates of hell. Our incoming gas line is a 12-inch round at 30 psi. So we in North Carolina are, I think, are the largest single point consumer of natural gas east of the Mississippi. Really large scale manufacturing. This is a dozen 4-inch gas lines that are just pumping out natural gas. It mixes with air. It heats up the crown, melts the glass. And then we have this massive furnace of molten glass. You get really optically clear. You float it on this bed of liquid tin. This is maybe 20 feet wide, 200 feet long, and these tridents that stick down from the ceiling are heating elements. So what we're doing is we're not heating the glass, we're controlling the rate of cooling to make it the right width, the right thickness, optically clear piece of glass. You cool it down to room temperature in this, 3 football field long line, and then we cut it up into big sheets of glass, 10 foot by 20 foot, 12 foot by 20 foot, massive, large sheets of glass. But that's all we do. We make big sheets of glass. Sometimes we process those, but we get really, really good at making those big sheets of glass. So as a result, we have started to lose that specialization and the loss of details that goes along with, if you make the glass and then make the insulated glazing unit and then install it and then make the windows, you actually understand what's happening in the industry. And we typically are 3 to 4 steps removed from consumers or from even installers. So that specialization in what we do really means that we're not connected to the materials and the materiality of building design or car design or all that sort of stuff. So the industry that I primarily service is the building industry, construction, mostly architect or commercial, but a little bit of residential. And we do a wide variety of things in that industry, a lot of specialty products, but the bulk of building construction and windows is actually a product called IGUs, or insulated glazing units. So this is 2 pieces of glass with an air gap in between. Again, not new technology. The first patents on this date back to 1865, 2 pieces of glass with a rope, and you just tar in place. Well, that insulating pocket in between there is like adding an extra jacket so you don't lose as much heat out of the building. So again, these had pretty early concepts where there was a product called thermopane, and that's what's shown in this top right. Here, the 2 pieces of glass were literally like fused together with a gunpowder reaction that would weld the edges of the glass together, which was pretty cool, as I hear. But this took way to this bottom right was another thermopane, which was a glass to metal weld. So if you think about an old incandescent light bulb where the glass actually goes right into the metal screw, that's how these 2 pieces of glass were welded together. So that technology was what was available in the 30s up into the 50s, 60s, and 70s. But it was really only a niche market. If you were, rich and you wanted a big picture window in your house, this was the product that you had. And back in the day, it was such an innovative idea that we actually had marketing materials to say, here's how you design your landscape because you're going to have a pretty window to look out. Or here's how you decorate your living room because your neighbors are going to walk by and check out this picture window. I mean, a picture window, just imagine it. It was such a big innovation that as a glass company, we had marketing brochures that looked at that. And it was because it was such a major innovation. Up until that point, you didn't have big windows in your house because it was just too cold. You couldn't sit within 10 feet of a single plate glass window in your house. In industrial buildings, it's different. You have heat generated from the process, or office buildings, they generate income so you can pay the gas bills. You couldn't do that in your house. But this technology, even back in the 1950s, it had a 20-year warranty on it, which is almost better than anything available today. So why isn't that what we still make today? It's because in the 1980s, the oil embargo came out and said, well, we've got to do something to reduce our energy dependence on imported oil. So where does the U.S. use most of its energy? 40% of it goes into building operations. Let's look at the next level. Where most of that energy get used? Heating, lighting, and air conditioning. So as a result, in the 80s, tons of regulation comes in and says, let's put in things to be more energy efficient in our building design. And that primarily meant we were going to see double glazed windows with at least 1 piece of low E as mandated. They're pretty much going to be required. And as such, this technology called IGUs replaced this kind of fused thermopane product. And that replacement, that IGU came in, it was designed like this. So instead of having a weld on the edge or a glass fusion, it's 2 pieces of glass. It's a spacer that's here. This is most times aluminum or steel. And then there's a primary seal here that is a PIB. It's a polyisobutylene, some sort of organic gluish material. And then there's a secondary seal that is silicone or something like that. And in between, there's air or argon or krypton. And the bigger the gas there is, the bigger the molecule, the less of them there are in there to do heat transfer. So it's a better insulator. So why did this technology take off? Because it was cheaper. It's easier and cheaper to make if you just glue these pieces of things together than have this high tech. And the first 5 years that these came out, the failure rates were like 10%, 5%. I mean, they're horribly performed, and they were made with cheap vinyl windows. So you had 100-year-old windows that you replaced with something that lasted 5. And so they've got way, way better. I mean, now there's a lot of 10-year warranty products, 20-year warranty products, but the better product got displaced due to cost. So we've had tons of innovations that have gone in this area. Glass coatings is another thing that we've had a long history of developing, and the coatings primarily go into windows as like low E, but it's been used in a wide variety. I'll share you with some of the technical applications, but not a new technology either. So the very first patents on this actually date back to World War II, and our company, like most, had to help the war efforts. And so we had pilots that would be up in dogfights and say, well, you know, the windshield in this plane is frosting up. What can we do? So this guy named Harold McMaster, who was an engineer for LOF, said, what if we put a chlorine-doped tin oxide on the inside surface? That'll reduce the emissivity. So low emissivity, low E, and was invented in World War II as a necessity to help windshields from frosting up in the windows. But again, this didn't really take off in commercial buildings until the oil embargo. But we, as a company, there's a couple ways you can make it. You can do a sputter coat low E, or you can do a hard coat low E, which is CVD, chemical vapor deposition. So that is taking gases, you react them in the tin bath in this inert atmosphere, and you leave metal oxides on the surface of the glass. And you put a variety of layers on to get it to do different functions. But this process, CVD, we are the world leader in this technology. We were one of the earliest innovators in the 70s and 80s. And we lead the way in this technology globally to make kind of unique and interesting products with this. And primarily what we're doing with this, again, in terms of commercial and residential buildings, we're trying to do things with these coatings to manipulate the properties of those things. And mostly it's trying to act as a filter or act as a radiator, but sometimes we put them on there to change the color or the reflectivity, or we add functionality. We add a conductive element, or we add a self-cleaning element, or we add some sort of antimicrobial element. And in terms of buildings, what we're trying to do, as I mentioned, most windows in your house are either a filter or a radiator. What we're trying to do here on the bottom right is the solar spectrum. So this is how the sun's energy comes into your house. And what we're ideally trying to do is cut out the UV, leave in all the visible daylight, and cut out the near IR. And that says if we do a good job of that and leave in all the daylight, you're going to have about 40% of the sun's energy still get transmitted into the building. So that's what we do today. The other thing that we try to do is we act as a radiator. So what we're trying to do, and this is sometimes the sun's energy, or it's sometimes the room energy. So if you don't want to lose the heat from your house in the winter, you know, we're taking the coatings, and instead of getting the heat transmitted through or absorbing in and then re-radiating through or back out, you know, in the winter, this is what would happen: is your room heat would just get transmitted through, or it would absorb it into the glass and then radiate out of the building. What we're trying to do is change the functionality to where we, instead of having transmission or absorption, we're reflecting that heat back into the room in the winter, or in the summer, conversely, we're reflecting the heat back out and not letting it come through. But that's primarily what we're trying to do with coatings. And this is the basic fundamentals of the science behind it. Is we're using what's called thin film interference. So the coatings that we put on typically are, you know, 10 to a couple hundred angstroms thick. So they're thinner than the wavelength of light. And if we put on a couple different layers of these, we can do what's called constructive interference. We can actually amplify those signals to make, you know, a little bit of reflection, more reflection. We can use destructive interference to take that and make it from reflection into no reflection. And you can see this when you have like an oil droplet on water. You know, why do you get this rainbow effect? It's because it's actually changing the color based on the thickness of the oil. And you use these refractive indexes and these interactions of these different coatings to actually change the functionality and change the aesthetics and performance of glass. So that's the kind of the science behind what we're doing. These coatings are really unique, and we can play them off of each other's layers to make really interesting functionality. So the key thing I tell people is, not all low E is the same. Not all coatings do the same thing. And these are all different types of low E coatings, and they look dramatically different, even if a lot of them have the exact same performance values. So it really is important to try and understand the aesthetic component of what we're doing, as well as the performance components of what we try to do. And we make with these coatings a wide variety of different specialty products. And those are the ones that I think, as artists, it might be really interesting. So there's a number of things that we do. The one that we do is we take a transparent coating. So most of your windows in your house or in your commercial building have a coating on it that's fully transparent. You see it through it and you might not even really notice it. Maybe you see a weird color or something like that. But the ones that we make are bendable, transparent, they're temperable. There's all these sort of things. But if you think about how that transparent coating can really then be used, is if you say that the coating becomes the wire, you can actually use that transparent coating to drive and to operate a number of different devices or functions. So this has been around a long time. It's been used in video gaming systems and solar cells and heated glazing. And the one that most people, have seen but may not be aware of is a commercial refrigeration. So for probably 30 years now, we use this on the inside pane of a refrigerator. So when I was a kid, you'd go to the grocery store, you'd open up the freezer, you'd close the door, and then the door would frost up and you couldn't read the types of ice cream for another 5 minutes. It would just take a while for that to get rid of the frost. So what we do now is these grocery stores take and put this conductive glass on the inside face. They heat it up just a couple degrees to get above the dew point, and that keeps the glass from frosting up. So why would a grocery store want to pay to heat up a freezer? It's because they want you to see the stuff that's in there when the door is closed. They want you to buy merchandise. So they might spend $2 a day heating up the door so that you can buy $100 worth of ice cream. That seems like pretty good economics, but that's the main reason behind, different types of heated glazing for that application. But when I think about the way that impacts potential design, people are starting to do all sorts of interesting and unique things. So one is this, what's called embedded LED display. So if you just take the coating and you laser etch a pattern into that coating, and then you embed like an RGB LED pixel, you put one of those every inch, and then you have a computer run that LED array, now essentially the entire building becomes a display. So these two pictures are the same building, and all they've done is put up a different picture on that LED. It's not projected. It's literally they're just turning on the LEDs just like you would turn a TV on and controlling those pixels. So you can play Tetris on the building. You can run a movie on the building. You can put your company logo on the building. But that sort of technology is really changing the way people are thinking about design and aesthetics and how to use glass and adding functionality. And it's driving a number of other technologies as well. One is called thermochromic and electrochromic paints. I'm not sure if I have a picture of that or not, but essentially when you put a current on some of these paints, they glow or they light up or they do different things. So you can use the current to drive a number of different technologies. One is what's called BIPV, Building Integrated Photovoltaics. So instead of having the glass be part of just a regular photo cell, a PV cell, that you put on your roof to generate electricity. What if the vision area of your window actually generated electricity? So we're seeing people start to do this now and say, instead of just reflecting the heat, we want to actually use that to create electricity. What about digital displays? We want to make the building into a display, or we want to put a touch screen behind that display. So we see people start to use this pattern, and you take that and etch a pattern into this conductive glass. And now you can use that grid to actually do sensing to make touch screens. You can use this to drive dynamic glazing. So what you're seeing here is this is a piece of glass, and instead of being static, it's always the same light transmission and always the same color. You can actually use two pieces of this conductive glass. So you think of it like a battery, the anode and the cathode. And then there's either some sort of solid state or gel material in between those. And when you apply a voltage change, it changes the state of what's in there. So it might darken it, it might make it opaque, it might make it whatever. And that's what you see in this picture. And they started to darken these cells here on the left, and the whole thing darkens up. So that makes the building more energy efficient because it's not letting as much sunlight in, but it makes it more comfortable. You can sit next to the window now. It makes it to where you have less glare on your computer screen. So it makes it, it's basically more usable space that's in there. So it's the conductive glass is driving a number of these different technologies. It's enabling this switchable technology. And another kind of interesting product that we make is called anti-reflective glass. So instead of a normal piece of glass, which is 8% reflection, 4 off of each surface, you can actually get about 1.5% by putting a destructive interference thin film coating on that surface. And essentially what you're doing is you're eliminating this coating and you're making less reflection and you're boosting your transmission. So if you laminate that together, you go from 8% reflection down to about 1.5% reflection. And this is the reason you might want to do something like that. What if you have a display, or what if behind your storefront, you want people to read the TV that's there? You don't want to have all that glare and oddity. So people are starting to do this for displays, and we're seeing it where people just want you to see what's in there as well. Kind of like the refrigerator, you want to see through what's in there. Well, if I have a storefront, I want you to see the stuff that's in the storefront. Or if I have a car showroom, I want you to see the stuff that's in the car showroom. And alternatively, this is one example. This is a stadium. And what they've done is they've made the press boxes with anti-reflective glass. And you can see here in this middle, this kind of white, like milky looking piece. Instead of having the anti-reflective coatings on the outside, they messed it up and they laminated it to the inside face. So now that's essentially what a regular piece of glass is. And this is the key thing when you look at some of these, is if I had a stadium, it was on one side of the road and it's all anti-reflective, another stadium across the street that's regular glass, you might not notice the difference between the two because you only notice this in contrast. But if you're actually in this stadium looking out at the game, you don't see the reflection of the overhead light behind you. You don't see the reflection of your yellow t-shirt or anything like that. You see the game, so it really does improve the viewing experience. It improves the viewability of these different things. And in this case, this stadium, what they did was in the spandrel area, they actually did it. This is the non-vision area of the stadium. They put it on the glass there because they didn't want the glare off of the glass that's in the non-vision areas to be blinding the players as well. So there's all sorts of kind of interesting ways that people are starting to take these coatings and use them in design to change the functionality, to change the aesthetics. So it's pretty cool and exciting. We've got a couple other products that are in the highly reflective family. So one would be mirror view. And essentially this is you just take a display and you hide it behind the mirror. So the display's off, it looks like a mirror. The display's on, it looks like a TV, and you can do this to change functionality. It gets used in a wide variety of applications where it could be people are looking at how long are you looking at the ads. So they put a camera on there and they actually are doing biometrics to see how long do you stare at the screen. And there's all sorts of kind of interesting things that are starting to take off. But this is a nice way to play with transmission and reflection and kind of mess with reality. There was an old thing that was called Pepper's Ghost. And this is how a lot of these optical illusions were done, back in the Wild Wild West days. And what they would do is they would have a mirrored piece of glass and they would look at a projected image and they would mess with the lighting conditions and make a ghost appear. The same function, same sort of thing, but now we're doing it in a much more kind of high-tech way. So there's all these different things that we're kind of doing to manipulate aesthetics and viewability with our products, which are pretty fun. And then there's loads of other products that we get introduced to. So insulated glazing, which is instead of air or argon, it's a vacuum in between, the embedded LEDs. Bird safe glazing, this is to keep birds from flying into the glass. Self-cleaning glazing, this is to keep you from having to go up and clean the windows. There's all these kind of emerging things. And one thing that we're launching probably in the next couple of months is a coating called Sanitize. And this is antibacterial and antivirucidal. So if you think about, the inside of your house and you want to keep the windows clean and you don't want to have potential viruses on there, or think about like a bus or a train that's a shared vehicle. How do you keep those surfaces clean from having viruses on here? Well, we've been for a couple of years now in development on these sort of products. So it's just kind of odd that we have this pandemic that happens to happen at the same time, but we have these products now that it can actually kill things on contact by adding different functionality on the surface. So just by using our products and using the different coatings, we can change the spaces that we're in terms of design, function, and aesthetics and performance. So it's really fun to be a part of all these sort of things. So why do we want to do momentum intersection? What kind of is interesting for us in this space, and what are we trying to accomplish? And there's a video here on our company on history and innovation, all these sort of things that you can check out at your leisure. But one of the reasons that I love doing this is when I look at glass complexity and windows especially, the world has got very complicated. So even in the 1970s and 1980s, we were one of two companies in North America. We essentially made 13 products. So this on the left is our catalog. That's all the products that we made and their performance. And in the middle here, this is our product samples. So this is anything we would send. That was all the products that we made, and we'd send it to an architect. They would choose one of those 13 pieces of glass. They'd cut it into a rectangle, stick it in a frame. That's how they made windows. And today, this is one of our customers on the right, using 2 pieces of glass with a piece of low E on the outside pane. These are all the options that they can offer you in that IGU. So there's probably 25 companies that make glass with coatings. There's different colors of glass. You can combine the inside with the outside. There are 20 different options. The outside is one thing, 20 different options on the inside, vice versa. You can add all these other functionalities. The world's really, really complicated in terms of windows for buildings today. So in just that little microcosm, it's super complex. Add in everything else, cars and displays and all these things. The world of glass is insanely complicated right now. So our company has a long history in innovation. But our current manufacturing, we are very structured. We hit a bunch of different markets, but all we do in that manufacturing plant is service that market, that product. And we're losing a lot of this hands-on experience. We're so far away from the market, we don't understand a lot of times what people are actually doing with it. What do they really care about? And so things that we're really good at, we're a great engineering company. Science and manufacturing, we do a very good job of that. Our online coatings, again, we're a worldwide expert. Our customer responsiveness, the customers that we serve, we will do an amazing job to bend over backwards to make sure that they're happy with the products that they're buying. And on process improvements, minor tweaks, reducing cost, improving throughput, improving quality. We're great at those things. At technical evaluation, we do a nice job. But where we have opportunities is we are risk averse. We don't like trying things for fun. We don't like trying things just to say, well, let's give it a shot and see if it works. We want to make sure that things work before we kind of launch them. Our experimentation, our R&D programs primarily focus on goal-oriented developments. So we have a window, we want it to do this, we develop a product that makes it do that. We don't just play and say, oh, that's cool. How do we use this? So we don't do those sort of things anymore. When we are so large scale, one of our manufacturing plants, we make 600 tons a day. If we wanted to just do a little test, we might make 50 tons of glass. We might make 10 years worth of inventory in a little test. So it's really difficult to do some of these things. And as a result, our speed to innovate gets slower and slower the more that we specialize. So we're actively looking at ways, how do we kind of, change this up a little bit? So what we want to do with this program is drive innovation. We want to reconnect with products. We want to reconnect with the materiality of what it is that we're doing and why that's cool. We want to see glass through new eyes and identify some different applications and say, this is a neat idea. And if we could do this, here is the path to this being a really nice product that might have commercial interest. And we want to work towards greater collaboration and do more technology sharing. When I look at the history of our company, Libby, Owens, Ford in North America, the names Libby, Owens, and Ford, those 3 guys spurred about a dozen or more different companies in Toledo. And then those have branched out to being glass industries that all around the country started right here in Toledo. And the way that they did that was they had tons of operators that worked in a variety of industries. They were artisans that had shops in their garage. They did their hands-on, and they weren't worried about IP and technology sharing. And we didn't have 100 lawyers working for us that made sure that we didn't talk to somebody else. They just developed cool stuff and worked with tons of people. And then as those developments came, they were fast. We created new things, and then it went in all sorts of different directions. So we don't have that today. So what I want to try and do is get back to some of those roots on where did most of our innovation come from, and how do we help drive the future of the glass city that we're in today. One of the other reasons that I like to collaborate is this is a nice comparison. And for some of you that are younger than I am, you may not recognize this. On the left-hand side, that's called a Sony Walkman. But back in the day, that was amazing. This was a really cool piece of technology. You could put these headphones on, put a cassette tape in there, and walk around and listen to whatever music you chose. That was a huge innovation because all you had was radio up to that point. And on the right, everyone knows the iPhone, I think. But why those 2 things? Well, it's because in the 70s, Sony could literally have one engineer that knew everything about how to make the Sony Walkman. So they understood injection molding of the plastic and what drove the sound to come out of that cassette tape. And if you took those apart, there's only 12 components, and the headphones are pretty simple. Literally, a couple engineers in one factory could make everything that's there. Think about the supply chain on the iPhone today. The glass is made by this person, who these people chem strengthen it, and then they send it to these guys, and they assemble it with this. There's no way, even Foxconn, which is massive in China. I mean, they're massive in buildings that employ tens of hundreds of thousands of people. The iPhone's too complicated for them to make all of it. So you have collaboration in this global supply chain. The world is just too complicated to not collaborate anymore. If you want to drive new technologies, you have to collaborate, and you have to work with a wide variety of people. So it's too complex to do alone. And what I see out of this is, if you look at idea generation, people talk about diversity and inclusion and all these kind of things as, some sort of HR initiative. When to me, as I see, if I have 100 people that are exactly the same carbon copies of me, and I ask them, I said, hey, let's come up with a new idea, I'm probably going to get 3 ideas. And if I have diversity and in the people that I'm talking to, and I have a wide branch of people that we're involved with, and we're collaborating with hundreds of thousands of different people, and they come from different backgrounds, and they have different stories, and there's all this diversity that we're getting involved with, I'm going to come up with thousands of ideas that are just better than working in a bubble. So I'm absolutely pushing collaboration to say, we as a company, it's the right thing to do, but it also drives better results, and it drives more interesting things to be involved with. And that's what I love doing. So that's the main reason for me. I really want to push these things and see this happen. So the last thing I'll leave you with is these mega trends. These are things that we work in the display industry, in the industrial, commercial and residential building industry, and automotive industry, and solar panel industry. But these mega trends are what's happening globally. These are what we see the world changing. Renewable energy, going to net zero, demographic changes. People are kind of urbanizing, and now with the pandemic, they're saying, well, maybe we don't want to urbanize. Climate change is happening. The sharing economy. Again, pandemic's changing this, but Uber and Airbnb and all these things where people are saying, why do I want to own a car if I only use it 2 hours a day? There's all these things that are happening, and that will drive innovation. That will drive new products, new uses, new demands of buildings and cars. And what I want to do is figure out what's needed as a result of these megatrends, and how do we help provide people with things that solve those problems, things that make those things better. That's what I want to be a part of. And the way that I want to do that is collaborate with interesting, smart, diverse, and talented people like you. And I want to come up with better, interesting ideas, and then figure out, how do we help solve the problems that people are trying to solve? Because if we do that, we will create, we will invent, and we will be a part of that solution and be around for another 200 years. So anyway, thanks again for your time. And if you have any questions of me ever, I'm always happy to go through things like this. As you can tell, I'm kind of a glass nerd. I love these sort of things, and I'm really interested to keep progressing this idea and this technology. So that's it. I'll stop sharing, and then I'll open up for Q&A. But thanks again for your time, and I hope you have a great week.